So a table to compare the kinds of bonds that you can find in the different organic molecules shown, the bond strength, bond energy, and the bond length. And you see that the relationship is the longer the bond, the weaker the bond. The shorter the bond, the stronger the bond. Now there are other elements besides carbon that can also undergo hybridization. Nitrogen, oxygen, phosphorus, and sulfur. These are common elements you can find in organic chemistry. Why do we hybridize these elements? Or why do these elements undergo hybridization? Even though they have lone pairs of electrons, we need to angle them such a way that they do not repel each other so bad. So for methylamine, we have nitrogen as a central atom. We have lone pairs of electrons that's not used for bonding, so they face outward, and the other three bonds are covalent bonds. We combine with carbon, hydrogen, hydrogen. We are going to use their sp3 hybridized orbital. So how do you know the hybridization of an element? You just have to use this rule that I give you, my own hack. The sum of the power of the orbital sp3 denotes s1p3. The sum right now is s1p3 means 4. 1 plus 3 is 4. 4 comes from 4 axes of bonding. Axes of bonding defined as lone pair and sigma bond. So for nitrogen, we have 1 lone pair, 3 sigma bond, total is 4. That's why you have sp3 hybridized. For methanol, oxygen, same thing. 2 lone pair, 2 sigma bond, sum of them 4, sp3 hybridized for this oxygen. And next, for phosphorus. Now, this double bond, but double bond has 1 sigma bond and 1 pi bond. We only count the sigma bond. So sigma 1, 2, 3, 4. There's no lone pair, so again the sum of this number is 4. sp3 hybridized phosphorus. In this case, your organophosphate phosphate group found in ATP, ADP, your energy currency. Now you may ask, this angle is not exactly 109.5, it is about 110. Slight difference, but we know that it's approximately the same because inherently the central element are different. So of course there's a slight variation between these angles, but they should not differ by a lot. Sulfur, 2 lone pair, 2 sigma bond, sum is a 4, sp3 hybridized. We find in methane thiol. Thiols are so smelly. This is something that we insert into the methane gas. Recall your school days in a laboratory lab, your methane gas turn it, oh, I can detect the smell. It's not because methane smells, it's because we dope it with something that's smelly, we can detect it. So that, oh, gas leak, teacher, we have some warning signs for our colleagues and friends. Same thing goes dimethyl sulfide for the S, sulfur, 2 lone pair, 2 bond pair. But interestingly, you see that the bond angle in dimethyl sulfide is about 2.6 degrees larger than that in methane thiol. Not surprising, because in your dimethyl sulfide, you have 2 methyl groups a bit bigger. Compared to methane thiol, there's only 1 methyl group. You see, like a crab with 1 claw compared to the other one with 2 claws. So there's more repulsion, and hence electron cluster bigger, they will spread, they repel more, and the angle become a bit larger. In this diagram, we show you the molecular orbitals of the hydrogen. So the MO theory, like chemist says, molecular orbital theory, is something very unique, and you need a lot of imagination to understand this. Now 2 times 1s orbital, okay, as wave function, remember they are expressed in also mathematical functions, formulas. When they come together, there's a chance that they can meet in sync. The wave overlap constructively and form a bond. That's how you get a sigma bonding orbital. But there's also a chance that they don't go aligned. You see, there's a mismatch in the alignment. You get a destructive wave, and then there will be anti-bonding orbital. My analogy will be 2 strangers come in, eye contact, friend or foe. I don't like you, You're not my friend. I have poor impression of you, anti-bonding. I don't form a friendship. Good impression, we can get along well, bonding. So two strangers come together, there's always a chance to be friends or foe. Now when two strangers comes in and they do not want to bond with each other, so you see there's a note here, there's no sharing of electrons, totally no contact. They don't look into each other's eyes. It's a very frosty relationship. But if they really like each other, they bond, see? Overlap of the orbital. You share electrons. Few electrons here. When you have two p orbital, it's the same thing. When they want to bond, perfect. Electrons shared in the middle, you have a pi bond being formed. Now if you do not want to form a bond, you always have a node. Node again means what? Regions of zero electron density. No electrons there, they don't share. Pi, anti-bonding orbital. Anti-bonding means not bonding. Now how do we draw condensed structures of molecules? We have to draw condensed structure because it saves us time. Okay, we don't have to show explicitly what kind of the bonds that the element forms because it's being understood by us. Carbon 4 bonds, hydrogen 1 bond, oxygen 2 bonds without charges. So for 2-methylbutane, you can read from the left to right. CH3, CH2, and then this carbon branches to two identical methyl groups, so we can factorize them, put them in brackets, bracket CH3, bracket 2, 2 times of it, so these are the condensed structure. You can do it this way or the other way with the bond sticking out here. Both are fine, but what you should know is translation from one form to the other. For skeleton structures, or we call it line bond structure, it is a very shorthand, time-saving measure, even better than just now. Okay, so we don't even put down some of the elements that's bonding to other elements like carbon here. Each junction, each band represents a carbon. Okay, and we don't even show hydrogen because carbon must have 4 bonds. So if I only show 2 bonds here, that means the last 2 bonds must be automatically hydrogen. So the 3 rules will be: the carbon are not usually shown because they assume. Hydrogen bond to the carbon are assumed, and atoms other than these two are shown. So you see for oxygen, I have to put down the H because this H connects to oxygen, not carbon, so I cannot assume. Nitrogen, same thing. I cannot just put an N here assuming that it connects to hydrogen. No, we can only do that for carbons and hydrogen. Here we invert to show the CC bond that this carbon connects to that carbon. So here same thing, CC. This part not inverted means I know that CH2, CH3, but the CH2 must be connected to this side because methyl group, so it must be the dead end. For this table here, you should be able to relate this skeleton structure and the calculate structure. You should be well versed in translating from one form to the other. Get used to this style, very important. It's a hint. Some work example for you. How do you interpret a line bond structure, the skeleton structure? So carbonate, a substance responsible for the odor of spearmint, has the following structure. Can you tell me how many hydrogens are there bonded to each of these carbon and give the molecular formula of carbonate? Give yourself some time. Okay, so now the strategy. Now first of all, we know that the end of a line represents the carbon. It always ends with a carbon, and carbon must have 4 bonds, so automatically must be 3 hydrogens, a methyl group. And the two-way intersection is a carbon with 2 hydrogen. So these are words you may want to copy, but to me it's easy to see. This part here, 2 lines means the last 2 bonds must be hydrogen. This carbon here, I see 4 lines, so there's no hydrogen connected to it. Same for this carbon. The last carbon here, I see 1 line, but it should have 4 bonds, so the last 3 must be hydrogen. So same thing, 3 lines shown, 1 line needed, hydrogen, 2 bonded hydrogen, 1 bonded hydrogen, 0, and 2 lines shown, so 2 hydrogens, 3 hydrogens. That's how you get the structure. Then you count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. C10. Hydrogen, sum of these numbers, 14. And don't forget your oxygen. So C10, H14, O, That's the formula for carbonate. Thank you. I'll see you later. Cheers.